In this video, I want to show you why a proof by contradiction works. Okay, so to do this, we need two key facts. And here they are. The first of these is that all mathematical propositions or statements are either true or false. There's no gray area. And the second is this logical equivalence. Now, the way we would prove this is with a truth table. But we've done enough truth tables, so I'm not going to prove this with a truth table. You'll just have to believe me that this is actually logically equivalent. If you want to check, go right ahead. I encourage you to do so. All right, so while I'm erasing this, let's think about what's going on here. All right, we want to prove a statement of the form P implies Q. So we want to prove if P is true, then Q is true. All right, so what we want is to prove that P implies Q is true. So another way to phrase that is to say that the truth value of P implies Q is true. If we could prove P implies Q is true with a direct proof, we would certainly do that. But if we can't do that, then we'd have to go about this roundabout way that I'm going to show you now. And that's another way to prove things. Often in mathematics, there are statements that we would like to prove by direct proof, but we just can't find that proof. It doesn't mean it isn't there. It doesn't mean that it doesn't exist somewhere, but mathematicians or human beings have not been able to find it yet. And so proof by contradiction gives us another way to get at what we want. To be sure that what we want to be true is true. All right, so we want P implies Q to be true. So what we do is we say, well, what would happen if P implies Q was false? So we suppose P implies Q has the truth value false. Now, because all mathematical statements are true or false, if P implies Q is false, that means that the negation of P implies Q must be true. All right, so let's recap a little bit. What we want is for P implies Q to be true. But we just don't know how to prove it with a direct proof. So we say, well, what would happen if P implies Q was false? Well, if P implies Q is false, then its negation must be true. This is because all mathematical statements are true or false. So if P implies Q is false, its negation must be true. So then we do some work using true mathematical derivations here. Each line follows from the one that came before, and we reach a contradiction. A classic contradiction is something like, say, 0 equals 1, or 0 is less than 0, things that cannot be true. So then we reach this contradiction, so then we must conclude that our original supposition, this right here, this thing that we supposed, must not be true. So again, to recap, we want P implies Q to be true. We say, what would happen if P implies Q is false? Well, if P implies Q is false, then its negation, not P implies Q would be true. Then we do some true mathematical stuff. We get a contradiction. And we say, well, if everything we've done in here follows the rules of logic, then we know none of those things could be incorrect. So what must be incorrect is that P implies Q is false. So P implies Q is not false. So it must be that P implies Q is true. Now, when we're doing this sort of proof, dealing with something like this, the negation of P implies Q is tricky. And so what we'll do is oftentimes we'll use, or really every time, we'll use the logical equivalence that I talked about at the beginning of the video, that not P implies Q is equivalent to P and not Q, to simplify our work. Okay, so this is the logic why of proof by contradiction works. Let me show you how you do it in practice. So you want P implies Q to have a truth value of true. You suppose P and not Q. Remember that since this is equivalent to not P implies Q, since this is equivalent to not P implies Q, what we're saying is that suppose P implies Q is false. And so then its negation must be true. All right, so in practice, what do? We want P implies Q to be true, so we suppose P and not Q. We do some work. We get down to a contradiction. The work we do in here is all logically correct, so that couldn't be the thing that led to the contradiction. So it must be that this is false, so therefore this is true. That's a proof by contradiction, or at least why it works.